Good morning, ladies and gentlemen. We want to continue with our encryption, and today, last time I remember we were doing a discussion on the RSA, and we covered quite a lot of issues, which I believe now most of you are in a position to tackle any problem that might have something to do with the RSA. And today we want to move forward and do the Diffie Hellman, right? As I have indicated, this is another example of an asymmetric key encryption. It's called the Diffie-Hellman key exchange algorithm. And before we proceed, I just quoted this statement by Bruce Schneier. He said, "It is insufficient to protect ourselves with laws. We need to protect ourselves with mathematics." So you are safer if you really appreciate your mathematics. It's not just an issue. It's not just a way of saying, okay, I need legal clauses to protect myself or to protect a certain people. No, rather protect yourself mathematically. There is power in mathematics. You will understand this better if you appreciate our encryption. Now, this is an algorithm which was discovered, I think, around 1977 by two guys, Whitefield Diffie and Martin Hellman, hence the name Diffie-Hellman. It's a key exchange algorithm, right, that is used to secure exchanging cryptographic keys, and this is done in a public key infrastructure or public communication channel. And you are going to discover that keys are not going to be exchanged per se, but rather they are going to be derived in a joint manner. Then you do exchange, and I mean, you will see how it's going to be done. But the most important thing here is they are not actually being exchanged, the keys, but we are going to derive them jointly. Yes, of course, some exchanges are going to be done, but the actual key which is used to do the encryption and decryption is going to be jointly derived. And we're going to talk about our two guys, that is our Alice and Bob. In some instances, we might talk of the server and the client. It's basically the same thing, but there is need for two communicating entities to agree first on the large prime number P, and also our base, a generator base that we might call G. In some texts, you're going to discover that they denote it with N. It's still one and the same thing. And this process must satisfy these conditions. In other words, the G that you're going to find must be greater than 0. At the same time, P must also be greater than your G. These are the two keys that we're going to discuss. And G and P will be in the public zone, right? Any Jack and Jill can have access to G and P. Doesn't matter, because the secret lies, or the security lies, on how you are going to be generating secret integers. These are just secret integers, not prime numbers, but secret integers. And for this algorithm to be very, very strong and secure, these values must be as large as they can be, right, to increase security. But for academic purposes, we're going to use smaller numbers so that it becomes easier for us to compute them. So both our Alice and our Bob, they're also going to generate their private keys, that is A and B respectively. Then, of course, there are certain calculations which are going to be done. So in simple terms, this is more like the algorithm which is used to do the process of encryption using the Diffie-Hellman. You need to know that Alice and your Bob need to agree on a private number P and base G that we said. Alice must choose a secret number A, and then soon after choosing this private number, Alice must compute this modulus function, G to the power A, or G raised to the power A mod P. Now, before I continue, you see, this is the public zone. This is going to be public, right? It's public. So in the public, we are going to have our G, we are going to have our P in the public. Then Alice must generate a key, a private key, that is A. At the same time, B must generate a private key, B. Then when they are done doing this, Alice must compute for GA mod P. And then soon after computing for GA mod P, this is sent to Bob. At the same time, G must also compute for G to the power B to its private key, mod P, and then that is sent to Alice. So this function is being sent to our Alice. These guys are going to have different functions now, right? So after computing for this, Alice now need to continue computing for B, this function which is coming here, right? This function, we can call it B. This function, we can also call it A. So now Alice is computing for B raised to her private key, which is A mod P. At the same time, Bob is going to use the key which has been sent by Alice, that is A to the power of B mod P. In other words, what are we saying here? We are simply saying the function, first, there are two things which are happening. The first thing is to compute for this, for these two functions. Aren't you? Then, after receiving certain keys, these guys also need to do these computations. So this function which you see here, this one, is equivalent to my B. This function which you see here is equivalent to my A. Then B is being raised to the private key mod P. The same applies to A being raised to the private key of Bob mod P. The answers that you get here must be equal. In other words, this must be equivalent to the shared key. And if the key is similar, then it means that is the key which is going to be exchanged. That's the long and short of our Diffie Hellman. That's the algorithm. This is exactly what I tried to do on this other diagram, whereby on the public zone we said we've got our prime number P as well as our generator, which is G, right? These can be accessed by any Jack and Jill, doesn't matter. But what matters most is how are you keeping your secret key. So, and I said for this to be more secure, P and G must be as large as possible. The same applies to the private keys which are going to be generated. Now you need to take note, Bob and Alice have exchanged positions. So we now have Bob here. So Bob is going to generate his private key B. But again, in the public, he's now going to have P, where he's having access to P and G. The same applies to our Alice. She's having access to P and G, but she has a private key which is A. Right. So the function which is being exchanged here is G to the power A mod P. Right? The same applies to this. The function which is being exchanged here is G to the power B mod P. Like that. Then, so you can actually use a certain notation to say GA mod P is identical to A, right? Then GB mod P is identical to B, just to reduce the function. So here the mathematics which is going to be done by Bob using the shared key from Alice is to say, okay, what did I receive? It's A, then raise it to my private key B, that is B, then mod P. The same applies to Bob, to Bob, yes, to Alice, who is on the other side rather. She's also going to say the key that I'm receiving from Bob is B, and let me raise it to my private key, then mod P. Now, what we are going to get here is answers. Here must be the shared key. After doing your math, your Diffie Hellman math, the key must be the same on both sides. That is confirmation to say this is the key that they're going to use. Okay, so let's do something so that at least maybe we'll appreciate this better. We've got our Alice and Bob. Let's say we are given P is equal to 23. Your G is equal to 5. Then we've got Alice here. We also have Bob on the other side. Now, Alice is being said to have generated a private key A. A is equal to 4. Then Bob is being said to have generated a key 3. So what's going to happen? Alice must compute for G to the power A mod P. The same applies to Bob. He must compute for GB mod P. Then your G, we are told it's 5 to the power A4 mod 23. The same applies to this. G, it's 5. Like I said, this is shared, right? This is shared. Right, never mind my handwriting. You know, it's difficult to use this. I always say it. This is going to do 5 to the power 3 mod 23. What do we get here? 5 to the power 4 mod 23. So we are saying 5 squared, right, divided by 23. The decimal is 1.73, right? Then we say 0.173 times 23. It gives you 4. Here you are having 4. Then on the other side, you have got 5 squared, which is 125 over 23. The decimal is 0.43. So 0.43 times 23, 0.43 times 23, which is 10. 9 point something, which is equivalent to 10. So what's going to happen is Alice is going to send 4 to Bob. At the same time, Bob is going to send 10 to Alice. Then Alice is going to use this 10 to compute again for the shared keys, for the shared key, whereby we said it's now this value that you got here. This was equivalent to what? To A. This was equivalent to B. So B was sent to, this is B, this was A. So we are now saying the B was sent and you raise it to your private key mod P. Then the same applies here, A being raised to the private key mod 23. Mod P rather for now. Mod P. Then B, that's 10 to the power A4 mod 23. Then A is 4, B is 3 mod 23. Right, if you do the math, we are now saying 10 to the power 24 over 23. The decimal part is 0.78. 0.78 times 23, you get 17.94 something, which I believe is equivalent to 18, right? Then let's do this one. 4 to the power 3, that's 48, right? That's 64 rather, sorry. Then over 23.783 times 23, that's 18.00, which is equal to 18. So tell me something. This key is the same key. So that's the shade key that we are trying to calculate. You'll be done with your Diffie Hellman. And it can easily confirm that you did the right thing or you did the wrong thing. You can march out of the exam, if it's an exam, knowing that, oh, I think I got this right, or maybe I missed something. So the pertinent question that I always get from students is Diffie Hellman symmetric or asymmetric? Diffie Hellman, like I indicated, it uses a private key, a private public key, right? There is a reason for this, to establish a shared secret, which is typically symmetric. But it's not a symmetric algorithm. It is asymmetric, but just that the algorithm uses some form of an established secret key, which is synonymous with symmetric algorithm, right? And the last thing, of course, is to cover the applications of our Diffie Hellman, especially in the secure sockets layer. Then you also have the SSH, the secure shell. Then it's also used in IPsec, as well as in most of these public key infrastructure. But the most important thing is to know how you are going to be keeping your secret key. Otherwise, I will wait for the discussions that we're going to be doing going forward. Thank you for your time.